Okay, share the screen again. Okay, let's get to it. So we started talking about the Klein-Gordon field. We came up with the Lagrangian, and the action is manifestly Lorentz invariant because indices are always contracted between upper and lower indices. And this Lagrangian does lead to the Klein-Gordon equation, which we made sure that it's a Lorentz invariant. So this looks like a good starting point to think about QFT. So that's exactly why we started to do that. And that is actually the theory that Heisenberg and Pauli developed back in the 30s, I think. So what we are supposed to do here is exactly the same thing we have done with the Schrödinger field. Once you have the Lagrangian, you identify the piece that contains the time derivative of the variable, and you differentiate the Lagrangian with respect to the time derivative to identify the canonically conjugate momentum. So what is conjugate to phi is del L del phi dot, which is 1 over c squared phi star dot. So that's the canonical momentum. And then immediately you know what the canonical commutation relation is. So phi and 1 over c squared phi dot star has the commutator of IH bar delta x minus y. So that's exactly the same thing we have done with the Schrödinger field. And as we have done with the Schrödinger field, you can write down the mode expansion to be consistent with this canonical commutation relation. And so that actually turns out to be this form, and we're going to justify this expansion later on. And you got this rather complicated prefactor, just like what we have seen in the case of the mode expansion of the electromagnetic field, vector potential, but the idea is still the same. So this is sum over all the momentum modes in a box, and then here's a normalization factor, and comes the annihilation operator for a definite momentum P, together with this wave factor of e to the IPX over h bar. And then I have another piece, which is the creation operator, B dagger, with the conjugate wave factor minus I p dot x over h bar. And here I'm assuming that phi is a complex field similar to the Schrödinger field. So that's why the phi is not Hermitian. If phi were Hermitian, and we will talk about that case later on, then this piece, the first term, its Hermitian conjugate is supposed to be second term to make sure the whole thing is Hermitian. And so in that case, the B has to be the same as A. So in that case, I have A e to the IPX over h bar plus A dagger e to the minus IPX over h bar. So B and A will be the same thing. But I'm talking about a complex field for now, then A and B are not the same because it's not Hermitian. So that's a situation we'll be talking about. So as a result, I have two sets of creation and annihilation operators. And the similar mode expansion of phi dot would be something like this. And of course, you also have phi star, then you have A dagger e to the minus IPX plus B e to the plus IPX over h bar, and also the same thing for the phi dot star. So I have 4 operators, phi, phi dot, phi star dot. And using this relativistic relationship between the energy and momentum, we know what the exact normalization factor is. And you do find, by using this canonical commutation relation, by putting in this mode expansion into the canonical commutation relation, you can figure out that the commutation relation between A and B are really that of the harmonic oscillators. So you have the commutation relation that AA dagger is Kronecker delta in momentum space. BB dagger is also Kronecker delta in momentum space. And A and B commute with each other. So they are totally 2 independent sets of the harmonic oscillators, or 2 independent sets of creation annihilation operators for particles. But both A and B have the common mass, because mass is already built into this expression EP in the normalization factor, which is a common factor for both A and B. So I have 2 sets of particles with a common mass. So that then we start to think about what could this second particle be. So how come that there are 2 sets of particles out of the single field, which have the same mass, but nonetheless totally independent from each other? So I can create A particle, B particle, totally independent from each other in my Hilbert space. but they have exactly the same mass. So the question is what's going on here? So that's something we need to figure out. And that actually turns out to be the idea that A describes a matter particle and B describes the antimatter particle. So that's where this idea called antimatter comes up in this course for the first time, namely that once you actually make the theory relativistic, there is this now new notion of antimatter in addition to matter. And that's a new concept that was not there in non-relativistic quantum mechanics, but now we would like to talk about that. So we are now thinking about the antimatter. Okay, so let me stop here and see if there are any questions about this slide.
I have a question.
Go ahead, Eddie.
So the Klein-Gordon equation in original quantum mechanics only work for spin zero particles. Will the field only apply to spin zero particles too, or does it apply more generally?
This applies only to spin zero particle.
Okay.
And I will discuss why later on.
Okay, thank you.
Okay. Any further questions?
Yeah.
Go ahead.
Before
Oh, sure.
we saw antimatter particles as like holes in the like infinite filled-up states, energy states of real particles. Is that like the same thing as this, or is this different?
This is different because this actually is a boson, and the idea of hole makes sense only for fermions. So when we actually talk about spin 1/2 particle, that is a Dirac theory. So in that case, it is a fermion, and the idea of antimatter indeed does turn out to be the same thing as holes. And so we briefly discussed it when we introduced the idea of hole earlier on in the context of fermion non-relativistic theory. So that idea works for fermions. But the Klein-Gordon field describes a boson with spin zero. So the idea of hole doesn't make sense because you can put arbitrary number of particles into the same state. And so talking about a hole doesn't make sense. So the antimatter matter for bosons is not associated with the idea of the hole, it turns out. But nonetheless, you can talk about antimatter. So that's what we are trying to discuss here. I'm not sure I'm answering your question. Am I?
Yeah, you did.
Okay, good. Any further questions on this slide? Excellent. So just by quantizing the complex Klein-Gordon field, we did discover that you have two sets of particles with identical mass. And now we try to identify this as the antimatter particle, and we need some evidence for that. So this is the same thing. And then this is a Hamiltonian now. So once you have the Lagrangian, you have done this in a homework problem before, you write PQ dot minus Lagrangian, that's a Hamiltonian. So in our case, PQ dot is that the phi is, let's say, Q, and this 1 over c squared phi star dot is P. So this piece is nothing but the PQ dot. But at the same time, phi star is yet another Q. Then 1 over c squared phi dot is P for phi star. So you need to actually add that in as well. So when you write PQ dot for both phi and phi star, I get the first time twice. Then I subtract Lagrangian from it. So I have this one twice. I subtract this Lagrangian. So I ended up with the first term once. And the remaining two terms here gets reversed in their signs because I subtract them. So that's how I ended up with this Hamiltonian. So the first term survives because I have this term twice minus 1, and that's how I get this one, this term once. Then the other two terms get reversed their signs because I'm subtracting Lagrangian. So that's the Hamiltonian. And now that I have this mode expansion, I can plug that in here. And you have done this algebra before too, which is kind of lengthy and tedious. So I'm not asking you to do this time, but end result is very simple. Namely, just you count the number of particles for each momentum mode. So that's A dagger PAP, and multiply with EP, that's P squared C squared plus M squared C to the fourth for the particle in momentum P. So you just count the number of particles in that momentum mode and assign the square root of P squared C squared plus M squared C to the fourth relativistic kinetic energy to each one of them. So that's a very easy to understand interpretation of the Hamiltonian. So it all makes sense. But once again, we have another contribution from this B particle in addition to A particle. Because B particle has the same mass m as the A particle, its energy is also given by the same EP, same p squared c squared plus m squared c to the fourth. So I have to add both number of A particles and B particles in the expression for the Hamiltonian. So this again all makes sense. So I still have the correct interpretation here that we have two sets of particles, A and B, of the same mass as a part of this theory of the complex Klein-Gordon field. So still, I haven't really justified why I should regard this as an antiparticle. And for this purpose, we now look at the charge of each particle. And if B particle were the antiparticle of A particle, they should have the opposite charges. So that's something we'd like to see on the next slides to make sure that this interpretation makes sense. But so far, I'm just confirming that we indeed do have these two sets of particles with identical mass contributing equally to the total Hamiltonian of the system. And so that's what we have done on this slide. And now move on to the discussion of the charge next. So to justify this interpretation, they are antimatter to each other. Okay, so let me stop here again to see if there are any questions.
In the case where you have, I guess, the particle being its own antiparticle and like A equals B, are you double counting, or is that,
No.
They're just?
That's a very good question. So it turns out that when particle is identical to its antiparticle, for example, photon is an example of this. There's no antiphoton, it's the same thing as photon. And a photon, of course, is described by the vector potential. It's not Klein-Gordon field, but the idea is similar. The vector potential is real or Hermitian as an operator. And when the field is Hermitian, then this has to be the same as a Hermitian conjugate, which means the second term has to be Hermitian conjugate of first term. That tells you B and A are the same. So sort of the general idea is that when you have a real field, then you have a particle which is identical to its own antiparticle. But when you have a complex field instead, then this part and that part don't have to be Hermitian conjugates to each other. And that's when you have particle and antiparticle. So here we are talking about the complex Klein-Gordon field. That's when you see two sets as particle and antiparticle. But when I go back and talk about the real Klein-Gordon field, then you have this constraint that B dagger is the Hermitian conjugate of A. Therefore, A and B are the same. Therefore, you don't have the second piece here, and you have only particle or antiparticle, the same thing as particle in that case. So that's an excellent question, and we will see that later on. Okay. Thank you for the question, Ali. Any other questions? All right. So here you see A and B have the same mass, and right now we have a guess that B should describe antiparticle, but now we are trying to see this by writing down a conserved current. So this is the conserved current. Conserved in the case of the four-dimensional theory is that when you do this del mu, which is, remember, a four vector, so the first component is 1/c del t and del x, del y, del z, and acting on J mu, which also has a time component, spatial component. That actually is the continuity equation. So I didn't write it here, but the time component of J turns out to be charge density times speed of light. So the del 0 J0 then is charge density times speed of light with 1/c del t acting on it. So C and 1/c cancels. So this is actually time derivative of the charge density. And spatial component of J is the current. And so del IJI summed over X, Y, and Z is a divergence of the current. So if you write this out explicitly in components, you find charge density time derivative plus divergence of the current vanishes. And that's nothing but the continuity equation. And if you integrate that equation for the entire space, then charge density integrated over entire space is the total charge in the system. On the other hand, the divergence part, using integration by parts, becomes a boundary term. You can drop it. if nothing is going on at the infinity of space, then you find the equation that the total charge is conserved. So that's why this continuity equation actually means that total charge is conserved, where total charge is defined by the time component of this quantity integrated over the entire space. And conservation of any the quantity originates from the symmetry of the theory, as Emily Noether told us, and Emmy Noether told us. And the symmetry in our case turns out to be the invariance of the theory to change the phase of the field. And if you go back to the Lagrangian we had, you can see that changing the phase of the field phi, that change is compensated by the change of the field phi star, because the phase and complex conjugate of the phase clearly multiplies to 1. So this Lagrangian does have this symmetry of changing the phase of phi. Just like what we had the symmetry for the Schrödinger field too, there also we had the symmetry of changing the phase of phi that did lead to the conserved current, and that had the meaning of the electric charge in the case of electron field. So it's exactly the same idea. For complex Klein-Gordon field, we have the symmetry of changing the phase of the field phi, just like in the Schrödinger field. And once again, that will lead to the conservation law. And that conservation law is what we are looking at right here in this continuity equation. And once you integrate the time component of this, the fork vector current, that leads to the conserved quantity. And that's also the same idea. For the Schrödinger field, the time component of the conserved current corresponds to the psi dag of psi. And the integral of that was really the number operator. So if the particle is charged, that gives you the total charge of the system. So we have the same idea here. So this J mu, I didn't put E here, which means that this really is the current of the number. And if you integrate the time component of this quantity, you get the total number of particles. So that's the idea, just like we had for the Schrödinger field. But now that we have this mode expansion of phi and phi dot, I can just put that in and compute the time in spatial integral of this quantity, which is meant to become the total number of particles in the system. But now I see this minus sign, A dagger A minus B dagger B. So this counts the total number of A particles minus total number of B particles. So that's a difference between the number of A particles and B particles. And if I multiply this by E, assuming that this particle is charged, then total charge in the system turns out to be total number of A particles minus total number of B particles, which means the charge of A particle is, let's say, positive, then the charge of B particle is negative. Therefore, A and B particles have opposite charges. Then you can conclude that this is indeed the antimatter. So A and B are particles of the same mass, but have opposite charges. And that's exactly what we mean by antimatter particle. So whenever we have a particle A of some mass m, it's accompanied by its antimatter counterpart of the same mass, but with the opposite charge. So that's what we call the antimatter. So what you see here is that just by looking at this action for the complex Klein-Gordon field, we could derive from the first principle that you have two sets of harmonic oscillators and therefore two sets of particles of the same mass, but with opposite charges. And that is now a prediction of this complex Klein-Gordon theory. So what we wanted to do is to basically promote the Schrödinger field theory to something that is manifestly Lorentz invariant. So we made sure of the Lorentz invariance by only contracting upper and lower indices. That's something you can now do mechanically without thinking too hard about it. So once you do so, you're guaranteed that you get a Lorentz invariant Lagrangian. So that's good. And that's what we have done. But once you have done so, you find a conclusion that this relativistic quantum theory has particle, but also antiparticle of the same mass, but opposite charges. That is now a prediction of this relativistic quantum field theory. So that's something we are learning on our way. So once you include relativity, many things turned out to be predicted. We didn't put in the antiparticle by hand, but it came out from this theory. So the relativistic quantum field theory in general predicts that there has to be antiparticle counterpart to every particle we have. So sometimes, as Adi asked, the particle and antiparticle may be the same thing, but sometimes they are not the same thing. For example, if the particle has an electric charge, obviously antiparticle has the opposite electric charge, so they cannot be the same thing. Then you have a clear distinction between matter and antimatter. So that's something we are learning now. So the minute we promote QFT to a relativistic QFT, then we have this prediction called antimatter, which turns out to be very, very generic prediction of the relativistic quantum field theory, which eventually became promoted to even a theorem called the CPT theorem. We'll come back and talk about later. I see something in chat from Chirag. How do we know that the charges are opposite of equal magnitude? That's because this is 1-to-1. So it's not A dagger A minus 2 B dagger B. You really just count the total number of A particles. That gives you the total charge. You really count the total number of B particles, and that gives you total charge with the opposite sign. So this is really 1-to-1, not 1-to-2 or 1-to-pi or anything. It's really 1-to-1. So A and B particles have the same magnitude of the charges, but the opposite sign, which is clear from this expression for the total charge in the system. Does that answer your question, Chirag? I see chat again. Yes, thanks. Okay, good. Any further questions on this slide?
Yeah, I have a question.
Go ahead, Natalie.
Is there not more than charge that is required to distinguish a particle from its antimatter particle? Because like in the case of neutrinos, like one of the biggest questions is whether or not the neutrino is its antimatter particle. But according to this argument, like we could say right off the bat that it is because it's neutral. And yet it's still a big question. So what other requirements are there?
That's an excellent question. So in the case of a neutrino, we are talking about something called the lepton number. So lepton is a generic name for neutrino, electron, and the heavier cousins like muon and tau altogether. And as far as we know, the total number of them, including all of these particles, 3 neutrinos, electron, muon, and tau, seems to be conserved. We have never seen a phenomenon where that total number changes. So at least from experience, this total lepton number seems to be a conserved quantity. If that's the case, then there must be a distinction between neutrino and antineutrino, because the neutrino is one of the leptons, so carries lepton number 1. Antineutrino is antiparticle, so has a lepton number -1. Then there's a distinction between the two. And we know that you have to include everything because, for example, muon can decay into electron neutrino, and muon neutrino. So only when you add all of them up, the total lepton number is conserved. If you just talk about the muon alone, it's not conserved because it decays. But it decays into muon neutrino, so muon lepton number is conserved, and then produces electron and anti-electron neutrino. And electron carries electron number 1, anti-electron neutrino carries electron number -1. If you add them up, that's 0, so that's conserved. So only after you add contributions from charged lepton and neutral lepton, namely neutrino, you get something conserved. So as long as this quantity is conserved, then neutrino and antineutrino has a distinction, and therefore they cannot be the same particles. But even though we haven't seen it so far, there could be a process that can change the lepton number. And that is a process people looking for. There are many people in a department looking for a process called neutrinoless double beta decay. So suppose you have a big nucleus like xenon. And suppose xenon undergoes double beta decay, meaning that you produce beta particles twice. And beta particle coming from a radioactive nuclear decay is an electron. So you're observing 2 electrons coming out from a nucleus. And that, of course, changes the charge of the nucleus from xenon to barium. And the charge, of course, is conserved. Electrical charge is conserved. But if that process happens, xenon decaying into barium with 2 electrons. Final state has 2 electrons, and therefore lepton number 2. Initial state was just xenon, no electrons and no other leptons, lepton number 0. So if such a process does get observed, that would be the discovery that the lepton number is not conserved. And that would be as shocking as discovery of the parity non-conservation by C.S. Wu, our Berkeley alum. She found this parity is not a conserved quantity in quantum mechanics in a nuclear beta decay. And that was a shock to everybody in the science community. So if lepton number will be found not to be conserved, then that's a huge shock because lepton number is not conserved. Therefore, as Natalie said, there's no distinction between neutrino and antineutrino anymore, which means there's no distinction between matter and antimatter in general. So that would be a huge shock. But that shock may be actually a good thing. And I'll come back and briefly mention that later on when I have time for it, maybe next week, that this may be actually the reason why you exist today. And then we'll come back and talk about this. So this is just a teaser for now, but it has to do with our survival against the complete annihilation. And it may be the neutrino who play the role of superhero to save us from complete annihilation. And that's why you exist here today. So we'll come back and talk about that. But that's an excellent question. So in the case of neutrino, there's still this big question whether neutrino and antineutrino are the same particle or different particles. And that question has to do with our own survival from the Big Bang. And so that will be a fun subject to talk about later. Did I answer the question to the extent we can talk about it now?
Yeah.
Okay, good. All right.
Thank you.
Any further questions? Okay, so we discovered antimatter. So, but as Adi asked already, one can also talk about the real Klein-Gordon field. And to have the correct normalization, it turns out that I need to put a factor 1/2 here to talk about real Klein-Gordon field. And so the real Klein-Gordon field is also expanded in momentum modes, just like the complex Klein-Gordon field. But now we have to make sure that phi dagger is the same as phi, namely real in classical language means Hermitian for operators. And for this operator phi to be Hermitian, then first term Hermitian conjugated must equal to the second term. So for complex Klein-Gordon field, I used to have A and B dagger here. But with the requirement of phi is Hermitian, then this second term has to be Hermitian conjugate of the first term, and therefore B is the same as A, and second term is A dagger. So as a result, we have the only one set of the harmonic oscillators, and therefore there's only one type of particle for real Klein-Gordon field. And immediately, what you conclude though, is that you don't have invariance to change the phase of phi anymore, because phi is real by definition. There's no way of changing a phase of real number. So phi cannot be changed its phase. Therefore, no, there shouldn't be conserved quantity associated with that. Indeed, when you look at this definition of the full current, there's a phi star del mu phi, but now phi star has to be the same as phi. In second term is del mu phi star phi, but this phi star also has to be the same as phi. And if you look at this, first term and second term are the same with the opposite sign, therefore they cancel. So this full current is identically 0, which makes sense because there is no symmetry, therefore there is no conserved quantity. Again, just like what Emmy Noether told us, symmetry leads to conservation law. When you don't have a symmetry, then there's no conservation law. So there is no charge associated with the real Klein-Gordon field. And that's exactly how this particle could be the antiparticle of its own due to the lack of charge associated with this particle. So in this case, A is an antimatter of itself, and therefore this is a neutral particle. So again, this is the same story. When you consider a complex field, then you are talking about a particle which has the antiparticle, which is distinguishable from the particle. because there is a number associated with the particle, and the antimatter has the opposite number, like charge in opposite electrical charge. Then you have a distinction between matter and antimatter. But when you talk about the real field or Hermitian field, then you're talking about a particle which is the antimatter of itself. And you're talking about the neutral particles. So that's what Adi was asking about before. Now you see the demonstration why charge is indeed zero, and therefore real field describes a neutral particle. So I hope that answers Adi's question. Good, Adi's nodding.
Yeah, so that factor of 1/2 keeps you from double counting in the.
Yes, that's exactly right. Thank you for the question. Any other questions about real Klein-Gordon field? Okay, so as I said, what you are seeing now is that we managed to promote Schrödinger field theory to a relativistic Lorentz invariant field theory, which was good. But that immediately led to a new prediction that the relativistic quantum field theory predicts existence of antiparticles. And so the promotion of the Schrödinger field led to a complex Klein-Gordon field that immediately led to a theory where a particle and antiparticle are different particle species. They are independent, but same mass and opposite charges. But we can come up with a smaller theory where the Klein-Gordon field is real, which we couldn't do in non-relativistic quantum field theory. But when you consider real field, now you have a situation where particle and antiparticle are the same species because it does not have a charge. So now you are seeing more varieties of different kinds of particles, which we didn't see in Schrödinger field theory. So the minute you go to relativistic theory, now you see this richness coming in and very clear predictions coming out. And so that we are learning already something just by promoting the Schrödinger field to relativistic version of Klein-Gordon theory. And that is already something new we have learned, namely the existence of antimatter. Okay, any questions on this slide? Looks like everybody's happy. Okay, the one thing we have to do, though, is that we have been using this box normalization all along by summing over all momentum modes quantized in a unit of one of the size of the box. But talking about a box specifies the reference frame where the box is at rest. So it's not actually a convenient notion when you talk about Lorentz invariant theories. And if you want to replace a box by infinite size universe, then you don't have the momentum modes quantized anymore, and you have to deal with the continuous momentum spectrum. Then you are talking about delta function normalization in momentum space instead of the Kronecker delta in momentum space we used to have. So we have to be a little bit more careful. So we switch to delta function normalization in momentum space, and then momentum is now continuous instead of discrete. And another thing we'd like to do is to treat space and time on equal footing. So what we have done mostly so far is to use the Schrödinger picture. In Schrödinger picture, the operators don't evolve in time, states do. But then we are treating space and time not on equal footing because the field operator phi is a function of position of space. That's why it is a field, but doesn't depend on time in Schrödinger picture. So we are treating space and time on unequal footing, and that's actually not very sensible thing to do in a theory with relativity. And instead, what we can do is to go to Heisenberg picture. And in the Heisenberg picture, states don't evolve with time, but operators do. Then phi is an operator, which already depends on x because it's a field operator, but that also depends on t too. It evolves in time. Now we have the field operator that depends both on x and t. And that is indeed the operator that follows the Klein-Gordon equation. Remember, Klein-Gordon equation has time derivative squared minus spatial derivative squared. That's a D'Alembert with 4 corners, which represent 4-dimensional space-time. So when you look at the Klein-Gordon equation, I actually hid that under the rug because I wanted to wait till this moment to tell you about this. Klein-Gordon equation already assumed that the field depends on time, otherwise it doesn't make sense because there's a time derivative on it. And that equation makes sense as an equation in the Heisenberg picture, where phi depends both on x and t. Therefore, acting D'Alembert on the field operator phi makes sense because it depends both on time and space. And D'Alembert is 1 over c squared del t squared minus grad squared. So it has derivatives both in space and time. And in the Heisenberg picture, that makes sense because phi already depends both on x and t. Then we can also write this mode expansion in a way that depends both on x and t in this 4-dimensional inner product p dot x. So it has p naught x naught, which is et, minus space p dot space x. So this exponent is now written in a Lorentz invariant fashion. It has a 4 momentum p and 4 coordinate x. That's exactly the form of the wave we have been using all along in quantum mechanics, namely e to the minus iet over h bar times e to the plus I p dot x over h bar. And time and space come with the opposite signs. And we have known this in quantum mechanics, but now you see that that comes out in this mode expansion because of the Lorentz invariance. So quantum mechanics, we didn't know that why there was a sign difference between energy and the momentum in the mode expansion. But now we know it actually originates from the relativistic Lorentz invariance. And nature knew about this, but we didn't know. But of course, because nature knew, quantum mechanics already had that built in, and the exponent was et minus px. And that's something that comes out automatically by solving the Klein-Gordon equation. So this mode expansion is now actually easier in the Heisenberg picture than in Schrödinger picture. In the Schrödinger picture, phi had the meaning of q, phi dot had the meaning of p, and we had to treat them independently from each other. That's why I kept writing both phi and phi dot independently, and neither of them depended on time. And because it didn't have time dependence in here, the initial condition for phi derivative had to be given independently from the initial condition for phi at a given time slice. That's why I had to write them independently from each other every single time in the Schrödinger picture. But now that in the Heisenberg picture, phi has time dependence already built in as a solution to the Klein-Gordon equation, I have to finish this. Then you can take time derivative with the t built in here. So I can derive phi dot out of phi. So that's actually easier. And then you can verify that phi and phi dot indeed satisfy the canonical commutation relation using this creationization operator. And that turns out to be actually a Lorentz invariant notion. But the only thing you need to be careful here is that dqp, which we have used in the phase space integral, always came with the size of the volume. So when you actually count the number of final state particles, what we did is do the phase space integral, namely x integral times momentum integral in the unit of 2 pi h bar. That's how we counted up the number of final states. But we can't use the box anymore in Lorentz invariant fashion. So instead of talking about volume times dqp, we need to find an expression which has a Lorentz invariant meaning, which turns out to be this combination. dqp over 2e is actually Lorentz invariant combination. And the reason is the following. When you had a box, and when you go to a moving frame, then size of the box gets squeezed by Lorentz contraction. So your box would look smaller. That's why it's not Lorentz invariant. But instead of talking about box, which is not Lorentz invariant, when you use 1 over E, 1 over E is 1 over gamma, this parameter in Lorentz transformation, gamma, gamma, beta, gamma, 1 over square root 1 minus C squared. So E gets bigger by Lorentz boost, and 1 over E gets smaller by Lorentz boost. By exactly the same factor, how much box would shrink by Lorentz contraction. So instead of having the size of the box, which is not Lorentz invariant, using 1 over energy is well defined for any given momentum. So it has the same behavior, but now this combination has a Lorentz invariant meaning. So that's why dQp over 2E is what we call Lorentz invariant phase space. But now that there's 1 over 2E as a part of the phase space integral, we need to be careful about the normalization of creation annihilation operator. And to compensate this 2E factor in the phase space, so A dagger commutation relation is in the delta function normalization, which is good. But in addition of the delta function, you also have this 2E together with it. So in Lorentz invariant relativistic quantum field theory, we do the mode expansion in this fashion, using the continuous momentum modes, because we don't want to rely on box. At the same time, we like to write the field operator in the Heisenberg picture so that we can treat X and T on equal footing. And then everything is kind of simple and nice because everything is now manifestly Lorentz invariant. The only cost we have to pay for this is that we have to accept a new expression for the phase space to make sure it's Lorentz invariant. And the cost of using this Lorentz invariant phase space is that A dagger commutation relation is not just delta function, but comes with this additional fact of 2E. So A and A dagger, roughly speaking, corresponds to creation annihilation of operator of creating 2E particle per volume. And A annihilates 2E particle per volume. So this normalization has to be dealt with a little bit more carefully. It still has the usual meaning of creation annihilation operator, but this normalization is something we have to keep track of when we do some algebra using the field operator, like computing the Hamiltonian, copying the charges, and so on and so forth. So everything follows in the same way as we used to do with the box normalization, but now we can do it in a manifestly Lorentz invariant fashion. We don't need to rely on a particular reference frame to define the normalization of these operators. Okay, let me stop here again. So any questions about this? So there's nothing conceptually new here. It's just that we try to deal with the field operator in a Lorentz invariant fashion. That's why Heisenberg picture is better suited for that purpose. And also we'd like to use this Lorentz invariant phase space. So in some sense, there's only a slight technical change from what we used to do with the Schrödinger field theory, but in a way that this is much more compatible with the relativity. And also that we don't need to deal with phi and phi dot independent from each other anymore, because single phi expression includes all the time independence already built in. So in some sense, everything is easier. So that's the what this slide is about. No questions? Okay. So there is one conceptual question I'd like to ask now. So now that we have the field operator in a relativistic quantum field theory, I'd like to see what the meaning of the field operator is. And for the Schrödinger field, the field operator psi of x had the meaning of annihilation operator of a particle at a definite position. And psi dagger had a meaning of the creation operator for a particle at a definite position. So psi of x, the x dependence, was really meant to be that you have creation annihilation operator at that position in space. So the position eigenstate had a very clear meaning for a non-relativistic quantum field theory. So we can ask the following question: what about the Klein-Gordon field? So when you act phi on the vacuum state, In the case of the Schrödinger field, which is non-relativistic, so this psi dagger creates a particle at position x. So we had this very clear correspondence to what we have done in quantum mechanics, not in quantum field theory. So psi dagger of x acting on the vacuum state had a meaning of the position eigenstate for a single particle in quantum mechanics. And we even derived time evolution equation for the states and saw that they had a completely identical set of equations for the time evolution of states. And that's how we convinced ourselves that quantum field theory is a good thing to be looking at. And it turned out to be even more useful than quantum mechanics, dealing with multi-body systems and quantum statistics. So that's how we basically made a conceptual advance to go from quantum mechanics to quantum field theory, making sure we had the same physics content. So we can ask the question if that would also carry over to Klein-Gordon equation. And the way we could make sure, indeed, that this psi dagger of x acting on the vacuum state has a meaning of position eigenstate is by computing this the inner product between the state created at x and state created at y. And psi dagger satisfy canonical commutation relation. So I can switch the order together with the delta function from the commutator. And that actually gave me this delta function. So that convinced us, indeed, that psi dagger of x acting on a vacuum state is really the isolated particle, really isolated position x point-like, and their normalization is given by delta function, namely that even if x and y are just a tiny bit apart from each other, they are orthogonal to each other. So they are different states, they are orthogonal to each other. So that's how particle had a very definite position when it was created by the field operator. So we like to test the same thing. I create a particle at position x by acting phi dagger operator on the vacuum state. And this is the Hermitian conjugate of the state, namely that's a bra, at a different position y. I want to see if they're really orthogonal to each other. But when you compute this, it's a messy integral, so I don't show it to you, but it's in the lecture note. And it turns out to be given by this the Bessel function, which damps exponentially, but not delta function. So the states you create at the slightly different positions are not orthogonal to each other. They have overlaps. And overlaps damps exponentially with the characteristic length scale given by the combination called the Compton wavelength, namely for a particle of mass m. If you use h bar and c, this combination has a dimension of length. That's why it's called Compton wave length. And with this length, this inner product damps exponentially. So roughly speaking, two states are orthogonal if the positions are different more than Compton wavelength, but they are the same states, more or less, with a big overlap when the positions are within the Compton wavelength. So that's something we didn't have in a non-relativistic quantum field theory. So this phi dagger of x is sort of creation operator at position x, like in non-relativistic theory, but not quite. It's not really point-like anymore. It's spread out a little bit by the Compton wavelength. And of course, when you go back to non-relativistic field theory, you send the speed of light to infinity, then Compton wavelength goes to 0. And this Bessel function reduces to delta function. So it has the correct non-relativistic limit. But as far as you keep the speed of light finite, which of course we know is finite, then states of particles at slightly different positions are not orthogonal to each other. So somehow particles are spread out a little. They are no longer point-like. So how do we understand that? And this is the explanation given by Landau's drift system. I'm going to tell you on the next slides. But here I'm just showing the large distance expansion of this Bessel function. Indeed, there's an exponential factor given by the characteristic length as inverse of kappa. Inverse of kappa is h bar over mc, that's the Compton wavelength. And in addition to this exponential suppression, there are also power suppression too, but of course, exponential suppression wins over power suppression. So exponential factor is much more important than power. So it's really true that states are orthogonal to each other, roughly speaking, when the distance is beyond the Compton wavelength, but the two states are the same when the distance is below the Compton wavelength. So the particles are spread out over Compton wavelength, and that they have the overlap when the distance is less than Compton wavelength. So that seems to be a new prediction. And in addition to antimatter we talked about, there seems to be a new prediction that the particles are now a little bit spread out by a distance suppressed by 1 over c, but nonetheless it's a finite distance. And so point particles are no longer, in some sense, really a point anymore. So slightly different positions still have overlap of the wave functions. So how do we understand that is the next question. Somehow relativistic particles are not localized, but smeared over Compton wavelength. You can also see that this is not only the relativistic effect with a finite c, but it's also quantum effect because distance is proportional to h bar. If you take a classical limit, h bar ascending to 0, the Compton wavelength goes to 0 too, independent of keeping c finite or infinite. So in that case, this reduces the point particle too. So this is actually a combination of relativity in quantum mechanics, which we haven't studied before. But having both relativity and quantum mechanics, we seem to find this new phenomenon that the particles are smeared over a certain finite distance of the Compton wavelength. So now we are trying to understand what that means in the next slide, based on what I learned from the textbook by Landau and Lifshitz. But anyway, any questions about this? So this general conceptual idea that the field operator was supposed to be a creation operator at a definite position. And if that interpretation is true, then this inner product is supposed to be delta function. But what we discovered with the Klein-Gordon field is it was not quite delta function, sort of delta function because it goes to 0 quickly beyond the Compton wavelength. But there seems to be some sort of finite range of distances where particles at different positions are not orthogonal to each other. So that's just a mathematical fact at this moment. And we will talk about physics of that in the next slide. Any questions about this?
I have a question.
Go ahead, Cameron.
So in the comparison to the Schrodinger field, you're considering basically just like the X vector being like position space, but in the case of this Klein-Gordon field, are you assuming X and Y also to be over position or space-time points?
Space-time as well. So here I'm actually taking this field operator at the same time. So this is the creating a particle at position X at a given time slice. And this phi is the creating particle at position Y at the same time slice. And I'm asking the question whether they are orthogonal to each other, and they are not.
Okay, but if you allowed them to be, instead of at the same time slice, at different time slices, could you show like for delta function?
Yeah, so if you go to the same time slice, you still see that you have basically things inside the light cone. And so within light cone, everything can be causal. But it turns out that this correlation function at a different times smears beyond the light cone a little bit, again, by the Compton wavelength. So it's the same phenomenon. So if you cut it at any time slice, so here I'm doing the equal time slice, but if you do it at an arbitrary time slice, then there is a finite range of space which is in the original light cone from the original point X to Y. And normally you would think that particles should stay inside the light cone because of the causality, nothing goes beyond speed of light. But this correlation function goes slightly beyond the light cone, again described by this Compton wavelength. So still, the particle seems to be smeared.
Okay. So for the points that end up going beyond the light cone, does it like exponentially decay back to the light cone? Or No.
So the behavior of this phi dagger 2-point function when x is at initial time and y is a later time is more or less contained inside the light cone as expected, but smears beyond light cone exponentially.
Okay. So I guess like what I was
okay.
yeah, no, I guess like what I was thinking is that like if you have something that goes beyond the light cone, that would be like faster than light travel in some sense. And so I was thinking that like in some case you would have some like exponential decay, like kind of converging back to the light cone line.
Yeah, that's an excellent question. So of course, causality has to be satisfied. And causality tells you that any measurement done at point X at a given time should not affect any other measurements you might do at a later time at point Y if this point Y is not inside the light cone, because you can't send any information to point Y. And that requirement translates to that any operator at initial time at position X and any other operator at the later time at position Y should commute with each other if Y is outside the light cone originating from X. Because if two operators commute with each other, you can talk about simultaneous measurements of both operators. And if you can, what it means is that measurement you have done at the initial time at position X is not affecting the measurement you might do at later time at position Y. So if the commutator vanishes, then that means these 2 points are not causally connected to each other. And indeed, when you compute the commutator of phi and phi dagger at different time slices, and then that vanishes indeed if two positions are outside the light cone. So causality is satisfied that way. But in terms of sort of the wave function you create, which you thought was a position eigenstate for a relativistic particle, is not quite point-like. It's spread out already at the initial time slice, and they are not orthogonal to each other. Causality is still satisfied because no measurements would affect each other if they are space-like separated. But the shape of the wave function itself is seemed to be smeared by this exponentially suppressed fashion. And so that's what I'm talking about here. So this notion that the particle seems to be spread out a little bit by the computed wavelength beyond the light cone actually is still satisfying causality requirements, but nonetheless, the particle seems to be spread out. And that's what I'm trying to say here. Am I answering the question, Cameron?
Oh yeah, that was really interesting. Thank you.
Okay, good. Any further questions? That was an excellent question. I really struggle with this when I was back in grad school. So that's why I'm trying to tell you what I learned when I struggled with this back then. All right, go ahead. Adi?
Oh, thanks. So does this smearing reaffirm that the Klein-Gordon field only works for bosons? Because it seems for fermions that would violate Pauli exclusion if they're kind of occupying a shared state or something.
It turns out that when we get to the particle spin 1/2 using Dirac theory, the same thing happens. They're also smeared out a little bit.
Interesting.
But again, in the case of fermion, you have to talk about anti-commutator, right? Just like what we did with the Schrödinger field. And anti-commutator vanishes when 2 points have space-like separation. So the causality still holds, but each particle is spread out a little bit. And it turns out that that spreading out has physical consequences called the Darwin term in the hydrogen energy spectrum when you actually look at the relativistic theory and look at the energy levels of the hydrogen atom. So it's a real thing. Thank you for asking that question. Any other questions here? So as I said, I struggled with this fact that the particles don't seem to be quite localized, and I wanted to understand what does it mean. And eventually I came across with the textbook by Landau Lifshitz that had a explanation in the introduction, the first chapter. So this is the shape of the Bessel function. So it dumps exponentially. It looks pretty local. And indeed, when you send this kappa inverse to 0, this does reduce the delta function, which you can verify. So if you integrate this over the entire space, if it's delta function, that gives you a finite normalization factor, and indeed it does. So when you send h bar to 0, namely classical theory, it reduces the delta function. Or when you send c to infinity, that's a non-relativistic theory, it reduces delta function. But as long as you keep both h bar and c finite, namely relativistic quantum field theory, then this distance is finite, and you have this exponential behavior, not delta function. And this is what Landau-Lifshitz told us. So this is actually delta function normalization I was trying to mention. So indeed, when you integrate over the entire space, this product reduces to a finite normalization factor, which means that it has the limit of reducing to delta function. But now the particles are not localized, so that's something we need to understand. And this is the explanation by Landau and Lifshitz. Suppose you have this relativistic particle here. But we know world is quantum mechanical, so you can borrow energy for a limited amount of time, as long as you can give the energy back within delta t of the order of h bar over delta e. So I can borrow energy to create a particle-antiparticle pair. So that costs me 2mc squared of energy. So I'm supposed to give the energy back within the time allowed by delta t over 2mc squared. So when you create particle-antiparticle pair, I have to borrow energy 2mc squared at least or more. And so I have to give it back within the allotted time given by delta t. So delta t is then limited by h bar over 2mc squared. But within that time allowed by uncertainty principle, particles can travel with speed of light, maximum, up to the distance of h bar over mc. So two particles cannot separate more than h bar over mc, but they can travel a little bit. So what can happen then is that here you create particle and antiparticle pair as a part of the quantum fluctuation within uncertainty principle. But the initial particle you had before can then realize that there is an antiparticle around it and decide to annihilate with it. So the particle you had initially is now gone. On the other hand, the particle that was born as a part of the quantum fluctuation now remains. And because this particle was initially created by the quantum fluctuation and could travel over distance h bar over mc, while the antiparticle created from quantum fluctuation annihilated the particle you had before, so it looked as if this particle has jumped from this position to that position within this Compton wavelength. And this is happening all the time when you consider both quantum mechanics, namely this uncertainty principle, and relativity, so that particles can travel within the speed of light. If you put both of them in, then it looks like the position of particle have all of a sudden jumped from here to there. And you are not able to observe this process of this particle-antiparticles pair, because that is within the uncertainty principle. You shouldn't be able to observe that fact. So the only thing you see is the end result of before borrowing energy, where particle was at this position, and after returning the energy, where particle is now at a new position, it looks like particle have all of a sudden jumped from one place to another, but this jump can happen only within this distance of h bar over mc, namely the Compton wavelength. And this is the explanation given by Landau and Lifshitz, namely that once you combine relativity and quantum mechanics, you have a new prediction called antimatter. And as we talked about, antimatter may be its own particle, but nonetheless, antimatter exists. And particles can be created in pairs. Particles can annihilate in pairs. And also that we know it's quantum mechanical. So quantum mechanics allows for this uncertainty principle. So uncertainty principle allows us to create a pair of particle-antiparticle by borrowing this energy of 2mc squared or more. And because you have to return this energy within this delta t given by h bar over delta E, this virtual pairs of particle-antiparticle can travel at most by h bar over mc. But when you return the energy you borrowed, you can return the energy by letting these virtual pairs annihilate back to the vacuum. That's okay, then the particle stays in the same position. But you can return the energy in a different way by letting the initial particle get annihilated with the antiparticle generated as a part of the quantum fluctuation. But then the particle created as a part of the quantum fluctuation is the one that remains, and therefore position has jumped by about h bar over mc. And this is happening all the time. So if you take a snapshot of this relativistic particle, at one instance it's here, next instance over there, next instance over there, it's like it's dancing all the time. And so that's why the particle is now a little fuzzy. So that's the intuitive explanation why the position of the relativistic particle is a little bit smeared out. And that's because of the consequence of the existence of antimatter, which we have learned, and also that there's an uncertainty principle, like we knew all along from 137. And if you just put them together, you immediately arrive at this conclusion that the position of the particle is a little bit smeared. And that is the origin why the position eigenstate which we thought should be localized, is not quite localized, but spread over this quantum wavelength. And this is a new phenomenon we would predict after the marriage of the quantum mechanics and relativity into a relativistic quantum field theory. So I hope this makes sense. Any questions about this? So I hope you see this is inescapable, right? Because only thing we used is the fact that antimatter exists. We learned it already. And another thing we used is that quantum mechanics has uncertainty principle. It allows us to borrow money as long as you return it within the allotted time. Just by combining these two facts, this is now the inevitable conclusion that position of the particles keeps jumping all the time within this quantum wavelength. And that's indeed what we have observed mathematically by computing the inner product of what we thought was position eigenstate at position X and what we thought was position eigenstate at position Y, but they are not orthogonal to each other within this quantum wavelength. And this is indeed an effect that appears only when you combine H bar, namely quantum physics, and C, namely relativity. So this is a specific prediction of the quantum field theory in a relativistic theory. Okay, any further questions on this? Okay, and so this fact that particles are spread out within quantum wavelength is indeed the origin of the Hawking radiation you might have heard about. So the Stephen Hawking, who unfortunately passed away, I think 2 years ago, made a prediction that black hole has entropy, namely heat, and it's emitting particles all the time because it has a finite temperature. And that's what is called the Hawking radiation. And to be fair, nobody has observed this because for the kind of black hole which we can observe in astrophysics are at least solar mass and so on. And it turns out the temperature of the black hole is related inversely proportional to the mass. For something as massive as the mass of the sun, temperature is so low that we were not able to observe the radiation because it's too low temperature, too cold. But anyway, so the Hawking made this realization that once you put together quantum mechanics and relativity very carefully in a situation near the black hole, he predicted that there should be this radiation coming out of it. And actual derivation is fairly complicated, and I don't attempt to do this. I actually even haven't done it myself, so I confess that I haven't seen the proof really. But conceptually, what we just talked about is sufficient to give us an estimate of this effect, why black hole has a temperature. So this is how it goes. So we talked about these virtual pairs of particles. Let's say electron-positron to be concrete. And we talked about the fact that there is an energy cost to create these virtual pairs of electron-positron by at least 2mc squared. And therefore, you have to return this energy within an allotted time of delta t given by h bar over delta e, namely h bar over 2mc squared. And within this allotted time, the particles can move over the distance of c times delta t away from each other. So roughly speaking, the distance between them is twice c times delta t. That's the Compton wavelength we talked about if you cancel factor of c from upstairs and downstairs. So that's the idea we already talked about. But imagine doing this near the horizon of the black hole. Horizon is the distance from the center of the black hole given by this expression. So this is the mass of the black hole, capital M, and this is the Schwarzschild radius, that's the size of the horizon. And at the horizon, gravitational field, I'm using non-relativistic language here, but it turns out that the modus works okay. So the gravitational force acting on the electron near the horizon would be given by this, right? So Newton's constant times the mass of the black hole times the mass of the object over distance squared is the force electron feels at the distance given by the Schwarzschild radius. And if I put in this expression for the Schwarzschild radius into this, I get this one as the force acting on the electron. But now that you created this virtual pair of A plus C minus and let them move by distance d, and if one of them falls into the black hole, then it receives the work given by the force times distance, and so that electron would gain energy given by this expression. Namely that by letting electron drop into the black hole, then you can return the borrowed energy by this amount. If this amount is bigger than 2mc squared, you don't need to let electron-positron annihilate again to give the energy back. But instead, you can give the energy back but just by letting one of the particles fall into the black hole. So if this FD can be bigger than 2mc squared, then you don't annihilate the pairs anymore. That particle would remain real because you have already returned the energy. And so uncertainty principle is satisfied. And then particle production is no longer within the quantum fluctuation, becomes a real pair production. And the condition for that to happen is that this FD is bigger than 2mc squared. And this combination FD is what turns out to be what is called the Gibbons-Hawking temperature of the black hole, TH. KTH is the energy, has an individual energy, times 2 pi, that's just a constant. So if the black hole has this combination bigger than 2mc squared, you can create pairs of particles. That's a Hawking radiation. So that will translate to the requirement that this is big enough. And if you cast that form of the condition into a different way of saying, if this Gibbons-Hawking temperature of the black hole is higher than the mass, you can create particles. So now you see a notion that the black hole has a temperature. So I didn't go through any complicated general relativity calculation here. This is just all conceptual and qualitative, but you really get this idea that once black hole is light enough, you can create real particles, which originates from this quantum fluctuation, but the gravitational field is so strong near the horizon, you can return this energy very quickly to make this virtual pair of particle-antiparticle into real pair of antiparticle, particle and antiparticle. One of them drops into the black hole, you don't see them, but the other one does come out, you do see them, and hence the radiation comes out from the black hole. And that criteria is the black hole should be light enough to make that happen, which translates to high enough Gibbons-Hawking temperature of the black hole. So this idea we just talked about with this interpretation by Landau and Lifshitz really does lead to this now prediction that black hole can radiate. It can make real particles that you can observe as long as black hole is light enough. And we express the condition in a different way, that if the black hole temperature is high enough, you can create these particles for real. And that's the idea of the Hawking radiation. So I hope this gives you some satisfaction. I'm sure you heard about this Hawking radiation somewhere, but now you at least see qualitatively what the criterion is, now knowing the relativistic quantum field theory. So that's what you're seeing on this slide. And I'm sure you got tons of questions here. Go ahead. No questions? I'm surprised. Don't be shy.
Typically, how much hotter does it need to be than like the surface of the sun, for example?
Well, electron mass is pretty sizable. So let me just estimate this. So that's a half MeV, that's MeV. And this is Planck scale over squared. So Planck scale squared over mass of the electron, 10 to the 19 GeV, Planck 10 to the 19 GeV electron. So that's 10 to the 19, 22. So that's 10 to the 22 times the Planck scale. On the other hand, the mass of the sun is Planck scale over proton mass squared. So that's 10 to the 38. So that would be 10 to the minus 16 of the solar masses for this process to happen. But of course, for the case of the photon doesn't have a mass, it has only energy. So even gamma rays can come out from the black hole as heavy as 10 to the minus 14 solar masses or so. Again, we haven't seen such a black hole, but the people do speculate that such a black hole might exist, called primordial black holes. And if such a black hole does exist, it might do the Hawking radiation. And that's indeed the way we have a constraint on these primordial black holes. If they are light enough, they shouldn't exist at the level of the observable gamma ray flux. But the solar mass black hole is much, 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 much colder than that.
Okay, yeah, thank you.
Any other questions? By the way, I can do quick estimates because I remember what we have done with the white dwarfs for the Chandrasekhar mass, namely that the mass of the sun is roughly Planck scale cube over proton mass squared. And if you remember that, you know what the mass of the sun is, and you can do this kind of estimate very quickly. So it's actually useful. So remember that formula, mass of the sun is Planck mass to the cube power over proton mass squared.
Can you explain how black holes actually lose mass? So I think a common explanation I hear is that it almost seems kind of suspect, but it seems like they're saying negative frequency modes go into the black hole, and so that would kind of contribute a negative mass term, and then it would kind of end up, because of conservation of energy, you want to just say that they.
Yeah, you don't need to actually use that strange idea. So now that if you accept the black holes at temperature, anything with a temperature leads to black body radiation by Stefan-Boltzmann law, right? So once you know the black hole has a finite mass and a finite radius given by the Schwarzschild radius with a finite temperature, you can compute the amount of radiation that comes out by using Stefan-Boltzmann law proportional to the area of the black hole. And that means it's emitting certain amount of energy per time. And that amount of energy should be lost from the mass times c squared of the black hole. That's the energy. And that's all you need to know. So what you can do then is to write a differential equation of m dot, how much mass changes, by Stefan-Boltzmann law from the area of the Schwarzschild radius per unit time over c squared, because the m is the energy over c squared. And once you write that equation, then you can solve it. And it turns out that the black holes are finite lifetime. So you don't need to refer to this funny negative frequency or anything. Just by knowing the black body radiation, you can compute the lifetime of the black hole. Does it make sense?
No, yeah, that does make sense. And I think you end up getting something like 10 to the 67, years or something like that. It's very
Some really,
long
really
time.
enormous lifetime for the
Yeah.
solar mass black hole. Yes, completely. Yeah, good. Thank you for that question. Any other questions? Okay, so that's about the Klein-Gordon field. We had a little fun. So the next thing I'm going to talk about is the fact that Klein-Gordon field has spin 0, but we also know particles have spins. So we need to generalize this idea of spin 1/2 and go to the Dirac theory. So that's the way we're going to talk about the relativistic field theory beyond this next week. Okay, that's it. Have a good weekend. And I post a new homework problem later today.
Thanks, Professor.
Bye.